In this example, we want to test whether the average age of adult coyotes in a certain region of Minnesota is more than 1.75 years old. We took a sample of 46 coyotes and found the average age to be 2.05 years. In this example, we have a sample standard deviation. We don't have the standard deviation of the population. So the hypothesis test I'm going to run is I'm going to test the claim that the average age of the coyotes is actually 1.75 years. And I want to see if my sample gives me enough information to reject that claim and instead to adopt the claim that the average age is larger than 1.75 years. So mu greater than 1.75. This is going to be a right tail test, and we're going to use a 1% level of significance, so my alpha is 0.01. Now in this example, the sampling distribution I'm going to use is actually the student's t distribution. And the main reason for that is that I do not know the population standard deviation. Sigma is unknown. Since I'm going to use a student's t distribution, I'm going to calculate a t-value, which is very similar to a z-value, with the exception of I use the sample standard deviation s instead of the population standard deviation, which I do not know in this problem. The t-value I calculate is 2.48, and remember that anytime you calculate a t-value, you need to add a degrees of freedom with it, which is the sample size minus 1. The degrees of freedom, again, basically give us the shape of the student's t-curve because the student's t-curve varies with how large your sample size is. Taking a look at a picture of the p-value we're going to find the area to the right of t is 2.48 with degrees of freedom 45. So for this I have to use my student t table. Now finding this p-value is a little bit more tricky using a table. What I need to do is go to my student's t-table, and the first thing I'm going to do is I'm going to go down the left column to the degrees of freedom that I'm using. This is basically like selecting the shape of the student's t-curve that I want to use. So I'm going to go all the way down to degrees of freedom 45. And again, this t-table lists values for t. It does not list areas in the main section of the table. So what I actually want to do is I want to scan this row and look for the t-value that I calculated. Now the t-value I calculated was 2.48. So I'm going to go back to my t-table and look for t equals 2.48. There's a high probability I'm not going to find it. But what I am going to find is I'm going to find where it would fall in between. So the t-values increase as I go left to right here. And I see that t equal 2.48 would fall between 2.412 and 2.690. So what I'm going to do is I'm going to go back up to the top of the table and look up the right tail area for each of these t-values right here. For instance, if I had a t-value of 2.412, going back up to the top of the table, I see that I have a one tail area of 0.01. If my t-value was 2.690, the right tail area for that would be 0.005. So the only thing I can conclude from this table is that because my t-value is in between these two, my right tail area must also be in between these two. Remember that as my t-value gets larger, as t gets further down the distribution, the area to the right is actually getting smaller. So I can say that my area to the right, my p-value, is between 0.01 and 0.005, with 0.005 being the smaller value. So going back to my example, you can see here that for my p-value, I've just listed it as a range. I don't have an exact number, but I have a range, and that will be good enough to make a conclusion on my test. Because I know since my p-value falls in between these two, really I'm just interested in what is my p-value less than. I know it's less than 0.01, which is what alpha is. So even though I don't have an exact p-value, I still know that it's less than my value for alpha. And so I'm going to again reject the null hypothesis. So what I'm rejecting in this question is I'm rejecting the claim that the average age of the coyotes is 1.75 years. And I'm going to adopt the claim that it's actually greater than that. And there is less than a 1% chance I would be wrong in rejecting that claim.